Um, Tim, you should be at your meeting with Mr. Stevens now. Just letting you know. Okay. All right, sorry. Back to problems here. Limit as x approaches 3. Hopefully all of these it's coming back to you really quickly. You should just look at the graph really quickly and answer these. We see that when x is 3, there is a hole. Remember, holes can have limits because the function from the left and the right is still approaching the same y value, which in this case is 3. So the limit is 3. The limit as x approaches 3 from the left will be this part right here, which is approaching value of 3. And then the last part here, limit as x approaches infinity. Remember, when the limit is approaching either positive or negative infinity, it's basically asking you for the horizontal asymptote. So if we look at the graph, as our x values are getting bigger, it's staying at this y value where the horizontal asymptote is at -2. So our limit is -2. It's never going to go below that line. Okay. Our limits graphically, you should be able to determine those with ease. Then we have our limits algebraically. So remember the first step, direct substitution. Plug it in, see if it works. So when I plug in 3, I get a 0 in the denominator here. So that tells me I can't do that as my first step. I need to use one of my limit rules. So one rule is that we can factor. So I can factor this to be x plus 3 times x minus 3. And that's being divided by x minus 3. So that will cancel, leaving me with the limit as x approaches 3 of x plus 3. I will plug in, do my direct substitution, and I get 6. Remember, notation-wise for limits, you should always be rewriting the limit part if you haven't done direct substitution yet. Once you do direct substitution, like we did here, you can then remove that limit part in the front. Otherwise, every time you rewrite the function, factor it, cancel it out, you should be writing limit right in front. So that way, whoever is reading your work can see that you are still finding the limit of that function. And it's not just a random function. Okay. Next one here, limit as x approaches 4 of this function. You want to just go ahead and do direct substitution right away. And when I plug in 4, nothing is going to turn to 0 in the denominator. So actually direct substitution is all we need to do in this case, even though it does look like a rationalizing problem because I see that square root. Sometimes you want to just kind of straight go into rationalizing, but remember, direct substitution first and see if that works. So this becomes the square root of 9, which is 3. 3 minus 3 is going to be 0. It's going to be 8 times 5 at the bottom, but it doesn't matter because 0 at the top means your answer is 0. Okay, so I didn't have to rewrite limit because I just did direct substitution right away. Please let me know if you have any questions as I'm going through these. I'm going to go through them kind of quickly because it is review, but there's going to be some parts where you might need clarification, so let me know. Number 4, it says find the horizontal asymptote of f of x. So remember I said earlier when we were looking at the graph that when we're trying to find the horizontal asymptote, we want to take the limit as x approaches positive infinity or negative infinity. So that's what we're going to need to do in this case, is actually take that limit positive infinity and then also the limit as our function approaches negative infinity. Now, algebraically, when we're finding horizontal asymptotes, we want to think about our 3 rules: top heavy, bottom heavy, same degree, and determine what is the degree in the numerator and the degree in the denominator to compare and figure out what our answer should be. This function in particular is a little more difficult because we have the square root at the top. So we need to kind of figure out what's going on here as x approaches infinity. So right off the bat, if I'm thinking about x approaching infinity, that's going to be like a huge number, right? Infinitely large number. So if I have, let's look at the denominator, 3x minus 5, that's like saying take a huge number, multiply it by 3, so now it's even bigger, and then subtract 5. Is subtracting 5 going to make any bit of a difference if you have that big of a number? No, not really, right? So we can think about this function as just 3x in the denominator. It still will be positive, that's true, right? Because x is approaching positive infinity, so that's still going to be positive. So we could just think about 3x in the bottom. And in the top, again, if we just look inside of the square root, 4x squared plus 7. We have a really, 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 really big number, and it's being squared, so that even that's going to be even bigger. And then it's multiplied by 4, so then it's even bigger, and then you're adding 7. Well, that 7 is not going to make too much of a difference, right? So it's like adding 7 more grains of sand to a beach. Is that going to really change anything, make a huge impact? No, not really. So we can think of this as actually just the square root of 4x squared divided by 3x. And the square root of 4x squared is just going to be 2x. But I will write absolute value around that because we know that it should be positive, right, underneath the square root. So absolute value of 2x and then 3x at the bottom. So we have a same degree in the top and the bottom, which means our horizontal asymptote will just be 2/3. Okay. So that is going to be our limit as x approaches infinity, x approaches positive infinity. Remember, for horizontal asymptotes, we also want to check the negative side. So this same kind of logic applies where this will basically become absolute value of 2x divided by 3x, but this time we're talking about a negative infinity. So if I were to plug in a negative number into this function, in the top it would still be positive, but in the denominator it would be a negative number. So this would actually be negative 2/3 as x is approaching negative infinity. So that is how we look at finding horizontal asymptotes. This was a more challenging problem, so I wanted to make sure and kind of go over that, how to do that. But you'll also see the different problems where it'll just be something more straightforward, like x plus 7 divided by x squared plus 2x plus 1. This is a bottom heavy function, so you know whenever it's bottom heavy, it's just automatically 0. So make sure you kind of go over those rules again. Make sure you got that. Bottom heavy is 0. Same degree is the ratio of the leading coefficients. Top heavy, it's going to be either positive infinity or negative infinity, depending on what you get when you plug in positive or negative values, kind of like what we saw here. So that is horizontal asymptotes. Number 5 says find the value of k that makes the function f of x equal to x squared plus 2 when x is less than or equal to negative 1, kx plus 4 when x is greater than negative 1, continuous for all real numbers. So we've got a piecewise function, and we know that one piece is x squared plus 2, so that's kind of something like this. But when x is less than or equal to negative 1, so it's actually more something like that, negative 1. And then we don't know exactly what that function is. We know it's going to be a diagonal line with the y-intercept at 4, but we need to figure out which k value, which is technically the slope of the line, what k value is going to make it so that that line connect with the other piece of the piecewise to continuous, because that's the only way it's going to become continuous is if they meet at the same point. So that's what we're going to try and figure out. In order for us to do that, right, the keyword is continuous. So we need to know, what does it mean for a function to be continuous? What is the definition of a function being continuous? And there are 3 things that we need to make sure are true. So the first one is the limit. Let's say if we're checking continuity at x equal to a, the limit as x approaches a of the function must exist. Remember, that rule needs to be the first thing that we check. Does the limit exist? Now, how do we check if a limit exists? Kind of like a sub-test here. The limit from the right side must equal the limit from the left side, right? So if those 2 limits from each side are equal, then that means the limit exists. So it could mean when a limit exists, say this is a, could mean there's a point there, or remember, holes are also limits. So at this point, if we prove that the limit exists, we're only proving that it's coming to the same y value, but it doesn't mean that it's continuous yet, because it could be a hole. So then the next thing that we need to prove is that f of a exists. So now we are proving that there's a point at that x value. It's not proven that the point meets where that hole could be. That comes in with the third step here, and that is the limit as x approaches a must equal f of a, because that's the only way that this point will end up filling that hole to make a continuous function. So that is our test for continuity. And that is what we need to make true for this function in this problem. So if we have a piecewise function, kind of like what we see here, that means that this left side here, that's the function x squared plus 2. That's the limit as x approaches -1 from the left. So I don't know why I didn't give enough room here. I'm going to try and squeeze what I can here. The limit as x approaches -1, since that's what we're trying to prove to be continuous. We know that x squared plus 2 is a continuous function, so we don't have to worry about any holes there. And we also know that this is a line which is also continuous. So the only point that we're worried about is x equal to -1, because that could be where the two functions either meet or they don't meet, and they kind of go, like it could be something like that instead. Sorry, that's a line, right? So we want to check the left side. So the limit as x approaches -1 from the left is going to be given by the function x squared plus 2. So the easiest way, just look there, x less than or equal to -1. So there's that. And we need the limit to exist because we want continuity. So the limit as x approaches -1 from the right must be equal to the left side. And from the right, it's going to be the function kx plus 4. So oftentimes with these questions, you should know the definitions, and the definitions, once you apply the definition, your answer will kind of just follow through. So here we use the definition of continuity to set up what we see here, the statement that the left side is equal to the right side. And then how do we solve limits? Direct substitution. So that's what we're going to do next is try that direct substitution. And remember that when we're doing this from the left or the right, you're still just plugging in. This is just -1 squared plus 2 equal to k times -1 plus 4. So now we have an equation where we can just solve for k. This is 1 plus 2 is 3 equal to -k plus 4. Subtract the 4, we get -1 equal to -k. So k equals +1. So that is the y value that we were looking for. Sorry, not y value, the k value that we were looking for. So when you plug it in here, right, basically the function x plus 4 is going to be the function that works to have these two meet here. Okay. So that is continuity. Next we have a tabular kind of question. Yes.
Is there any chance that you could post these notes on the Google spreadsheet?
Yeah, I'll be putting them on the spreadsheet, but I also just put a folder on Schoology with these notes.
Oh, okay, cool. Thank you, Miss Martin.
You're welcome. So yeah, we have 2 more problems, so we're good with time. We have this function here, f, but they've only given us a few values of f. So we have the 2 points here, -2, 3, 2, 2. And it is asking us the equation f of x equal to 1 must have at least 2 solutions in the interval from -2 to 2 if c has what value. So basically, if I were to kind of draw this out, we have -2, 1, 2, 3, 1 point there, 2, 2 is the next point there. And then we have this point 0c. So we know that it's going to be a point that has the x value 0, so it's going to be somewhere on that y-axis, but we want to know what value of y is going to make it so that when f of x is equal to 1, so meaning y is equal to 1, there's two solutions. So if you think about it, we don't really know what's happening in between those 2 points that we have drawn. There could be like an infinite variation of things that could happen. Like maybe it's just a straight line connecting the two. That would mean there's no solutions for y equal to 1 because it doesn't go through that line. It could be something like that. Again, that would mean there's no solutions. It could be something like that. And in that case, it crosses through that line twice. So that would mean we have at least two solutions. It could be something like that, right? It could get crazy. So that would be more than two solutions. This is 1, 2, 3, 4 solutions. But it's at least two, which is what they want us to figure out. This is actually a multiple choice problem. So I will give you the options here. And D, 4. Okay. So thinking about what I just said, the examples that I just showed you, would C be able to be 4? 4 would mean it's got to be a point right up here. I connect that. Does that work? No, it doesn't go through the line y equal to 1. So that cannot be an answer choice. Does 3 work? No. Would 1 work? It goes through the line, technically it intersects it, but only once, so that would not work. So it would have to be 1/2, because if it's 1/2, then we see that it crosses through twice. So correct answer is 1/2. And what theorem are we technically using here? The intermediate value theorem. How is it that we're using this theorem? Well, the theorem says if you have a continuous function, oops, that's the key word, it's a continuous function. Because otherwise, if it was not continuous, then we wouldn't know that there's at least two spots, because what if the function happened to be discontinuous at those exact two spots, right? You guys remember that circle activity that we did when we removed the circles and we saw if there is a hole or not? If we know that it's continuous, then we know that that's not going to happen. So by the intermediate value theorem, which says that if you have 1 point above the solution and 1 point below the solution, and you know that it's continuous, then we know that there will be at least one solution. And so since both of our endpoints are above that solution and we have this one solution here, we know that there will be at least 2 times where it will cross through that line. Okay, so that's the intermediate value theorem. That's how we kind of apply it logically there. And then we have this last problem. The limit as x approaches 0 of x cubed times sine of 1 over x. If I do direct substitution right away, that's like a red alert. It's undefined. So we can't plug an undefined function into sine. That just doesn't give us any solution. So we need a workaround here. We can't factor, we can't rationalize, we can't do any of those other limit properties or rules. Then what can we do to figure this out? Well, what do we know about sine functions? We know that they're gonna oscillate, but they're not going to go past 1 or -1, right? So I know that sine of 1 over x is going to have to stay in between -1 and 1. Now, we're trying to find the limit with x cubed times sine of 1 over x. So I'm just going to go ahead and multiply this whole thing by x cubed. So now we have negative x cubed times x cubed 1 times x cubed is x cubed. So in the middle, we have the function that we're trying to take the limit of. So we can take the limit of this whole line here. Limit as x approaches 0 all the way through. So that you can see that in the middle, we now have the problem that we're trying to solve that we can't just yet. But on the left and the right, we have limits that we can do direct substitution. If I do direct substitution, I get 0 and 0. So we have a function here, limit as x approaches 0 of x cubed times sine of 1 over x. And that value is between 0 and 0. Well, 0 and 0, that's the same thing. So if you have something that's in between the same thing, what does it mean about the thing that's in the middle? It has to be the same thing. So we were able to solve this problem here. This is going to equal 0 using what we call the squeeze theorem. We practiced this before. We basically set it up knowing that sine, or if it's cosine, knowing that cosine, both of those are going to go between -1 and 1, right? So that's what we're squeezing this function in between, and then we can multiply by whatever we want in order to make it look like what we're taking the limit of. So in this case, we multiplied by x cubed all the way, and then we took the limit as x approaches 0 so that we can figure out what is squeezing this function, and then that becomes our limit. So this was just kind of like a quick overview of the different limits and continuity topics and kinds of questions that you may see on the AP exam. The free response questions are going to be kind of bits and pieces of a lot of different things. So it could be like a piece, like number 5 could be a piece of one of the free response questions. So we didn't do like a full-on free response question. Remember that you can check on AP Classroom. They have lots of practice there, and you can check it out by unit. So look at unit 1, see if you can try a free response question after we've kind of reviewed all of these different approaches. And let me know if you have any questions. Remember, I have tutoring today from 12:30 to 1:30. So you can stop by. We can go over either your assignment or start reviewing, ask any questions you may have. But that's going to be it for today, people. Yeah, perfect timing, actually. Let me know if you have any questions. Otherwise, everybody have a wonderful, beautiful day. It looks really nice outside. The weather looks nice. So make sure you take some time to go outside, and I'll see you all tomorrow.
Miss Martin, thank you.
Bye. You're welcome.
Thank you, Miss Martin.
You're welcome. Bye.